Welcome to everybody. Yeah, good morning, good afternoon. Yeah, it's a pleasure. Yeah, to be here again. And what you see in my background, yeah, here is my finger. Yeah, is inside the tunnel of the VLTI, so the Very Large Telescope Interferometer. Yeah, and what you see, the rails. Yeah, and on the rails there are, well, at least, yeah, you see two carriages, and on the carriages are mirrors, and these carriages are moving as a function of the position of the telescope in the sky, just to compensate, yeah, for the difference in the time arrivals of the signal along different light beams. Yeah, so, well, it's a very impressive place in the heart of the VLTI, because these carriages, yeah, are moving with an extremely high precision, yeah, fraction of a micron, yeah, precision, and this during tens of minutes, the time, well, it takes, yeah, for a star, yeah, to pass through the meridian and go to another location. Yeah. So now lecture number 5. Yeah, I will just share my screen with you. So it's an open board presentation here. Can you see it? What I will start first with, yeah, is just a summary, yeah, of important relations that have been derived during the previous lectures. Yeah, and well, the first one is the following. Yeah, last week, yeah, we looked at the two holes Young experiment in the context of a quasi monochromatic light. Yeah, and if we assume that the difference in the arrival times of two beams, yeah, in the focal plane is less than the time of coherence, which is defined as 1 over delta nu, where delta nu is a bandwidth, yeah, uh, through which we are observing, yeah, then we've seen that the distribution of intensity, yeah, in the observer screen, yeah, was well, a kind of sinusoidal distribution, where this factor here is known as a module of the complex degree of mutual coherence of the light. Yeah? And what we showed is that if you relate, yeah, this small time delay between the arrivals of the two light beams as a function of x, which is in fact an abscissa along the direction connecting the two holes, well, parallel, yeah, to the direction connecting the two holes, then you get, yeah, the light distribution in the observer screen. Yeah? So we see a very important quantity which comes is the module of the complex degree of mutual coherence. Yeah? Now, so this is a distribution you obtain as a function of the abscissa x. Yeah? And now what we have seen is that if you, well, a very important quantity, yeah, is a measurement of the contrast of the fringes, yeah, which is known as the visibility. And if we calculate by means of this formula, what it comes out, yeah, we just find that, well, it's just a module, yeah, of the complex degree of mutual coherence. Yeah. So we have a direct way, yeah, by measuring the visibility of the fringes, yeah, to know what is a module, yeah, of this expression. Now, more generally speaking, yeah, the complex degree of mutual coherence, yeah, is a complex quantity. Yeah, it means that it may have a real part and an imaginary part. Yeah, and it is defined as the following quantity. It's a time average, yeah, of a correlation measurement between the electric field, yeah, at the two holes, yeah, and divided by the average intensity of the light. Now, what we have seen during the previous lecture, yeah, is, well, we derived, yeah, the so-called Van Sittard-Zernike theorem, yeah, and in the framework of the Fraunhofer approximation, yeah, which is an approximation in which we assume that the size of the source and the distance between the two holes is much smaller than the distance between the interferometer and the stellar source, yeah, then we have derived, yes, this very important result that the complex degree of mutual coherence is merely the Fourier transform of the distribution of the normalized intensity of the source we are looking at. Yeah? And well, UV, yeah, are space frequencies, yeah, which are simply defined as follows. It's x over lambda for U and y over lambda for V. So what is x? I remember is the x coordinates. What's the distance, yeah, along the x-axis between the two apertures or the two holes, yeah, and y is of course, yeah, along the ordinates, yeah. So is the distance. Then you divide this by lambda, and you get, yeah, I've demonstrated last time, yeah, the equivalent of a space frequency, yeah, angular space frequency. Okay, well, when we find this result, yeah, what comes to our mind, yeah, is of course to do the following, yeah. We know that by an inverse Fourier transform, so this is an inverse Fourier transform of the mutual, of the complex degree of mutual coherence, yeah, we will retrieve, yeah, this normalized specific intensity, yeah. And the normalized specific intensity, yeah, is just a specific intensity derived, yeah, by its integration over the whole source, yeah. So that when you integrate this one over the source, you find that it is equal to 1. Okay, so let's just well, spend a little more time, yeah, on these two expressions. So the first expression tells you that the complex degree of mutual coherence is just the Fourier transform of the unknown, yeah, normalized specific intensity of the source, yeah, over the sky. And what we are interested in is, in fact, to retrieve this expression, yeah, with an angular resolution, yeah, which is defined by, well, the inverse of these space frequencies, yeah. So which would be lambda over x and y over lambda over y. So you remember the baseline divided by lambda gives you the angular resolution, yeah, of the interferometer. So to do that, to retrieve this quantity, which is unknown to us, whoa, we see we just make, yeah, the inverse Fourier transform of that quantity, yeah, and if you have sufficient number of measurements of the complex degree of mutual coherence over the UV plane, yeah, we will able, yeah, to get an image of the source with an angular resolution which is equivalent, yeah, to the largest baselines that we have in our interferometer. Okay, now, well, I hope that all of you, yeah, had a look, yeah, at the fifth YouTube video lecture, yeah, which is the subject of the lecture of today. And what I would like to do, we'll move this here. I would just take a mask here to make things too complicated. Just put the mask here. Yeah. So, well, in that lecture, yeah, there are many applications. Yeah. Well, we try to find what is a complex degree of mutual coherence due to, well, a delta function, which is a point-like star. Yeah. Then of a double star. Then the proposition was to look at the case, yeah, of a star which is square. Yeah, square means that, well, it's of course imaginary star in the sky which shape is square. Yeah, and then well, there was a long demonstration for the case of a star which has a circular shape. Yeah, and this is the most difficult demonstration. Yeah, which leads to the result, yeah, of finding that the complex degree of mutual coherence in that case, yeah, is the Bessel function of first order. Yeah. But as I said before, yeah, things are much more simple, yeah, if we consider square aperture, square stars, everything square, yeah, and it's what I invite to do right now, just to make the exercise with you for the case of a square star, yeah. So, well, a square star has its specific density as a function of the angular coordinates, yeah, zeta and eta. So you could say, okay, that zeta is along the x-axis, yeah, and eta along the y-axis, yeah. But these are angular scales, yeah. So what would be a good representation for that intensity distribution? Well, first a constant, yeah, that we will fix in a moment, times the Dor function of zeta divided by zeta zero. So zeta zero, yeah, is the angular size of one side of the square, yeah. So along zeta, it is zeta zero, and along the eta direction, it's also zeta zero, yeah. So it's a square, yeah. So I just multiply, yeah, this constant by the Dor function of zeta divided by zeta zero, and by the Dor function of eta divided by zeta zero, yeah. So I know that the Dor function is equal to 1, yeah, if the module of zeta is smaller than zeta zero divided by 2, and the same for the coordinates eta, yeah. So the Dor function along the eta coordinates, yeah, is equal to 1 if eta, the module of eta is less than zeta zero divided by 2, and 0 otherwise. Now I would like to fix the constant because, as I said, we are going to use, yeah, the normalized, yeah, intensity distribution, which is this quantity given by equation 9 divided by its integration over the coordinates. Yeah. Now, well, it's quite obvious, yeah, that the normalized, yeah, intensity, yeah, will be, of course, equal to that expression divided by the angular size of the star, yeah? But the angular size will be zeta zero times zeta zero. So it will be I zeta divided by zeta zero square, yeah? So the value of the constant, yeah, is equal, in fact, to 1 divided by zeta zero square. Now, if you would like to make that derivation analytically, yeah, just take, yeah, this expression into this one, and you will find this result, yeah? So this is quite obvious, but also intuitively normal, yeah? Then we will find successively, yeah, that the module, yeah, no, that the complex degree of mutual coherence is equal to the Fourier transform of that expression, yeah? So it is the Fourier transform of this Dor function multiplied by that Dor function. Now, the constant of proportionality, 1 divided by zeta zero square, yeah? Well, we have seen that we may take it, yeah, away from the Fourier transform, yeah? And this Fourier transform depends, of course, on the space frequencies u and v. Now, we will make use of a property that we have derived last time, yeah, which is a separation of variables, yeah? So we find then that the Fourier transform of this, the multiplication of these two functions is just equal, yeah, to the multiplication of the two Fourier transform of the independent Dor functions, yeah, because we may separate the variables, yeah. This is the reason, yeah. Of course, you may demonstrate, you know, once more analytically this property. It's so easy and very obvious, yeah. So what is the difficulty now is to calculate, yeah, what is the Fourier transform of the Dor function. But this we've seen, yeah, last time, that the Fourier transform of the Dor function, yeah, is a sinc function, yeah. You remember sine of pi times u divided by pi times u. But here we don't have zeta, we have zeta divided by zeta zero, yeah. And here we make use, yeah, of the similarity properties, yeah, that we have demonstrated, yeah. Well, it is in the lecture notes and in the video. That the result will be what? Will be 1 over zeta zero square. Now, the Fourier transform of this function, yeah, Dor function, yeah, is sin pi times u, but times zeta zero, because you have here a zeta zero in the denominator, yeah, divided by pi zeta zero u. And the same, yeah, for the other Fourier transform. So now there is a nice simplification. We see that the zeta zero square here and the two zeta zero here in the denominator go away. And we find that the complex degree of mutual coherence, yeah, of a square star, yeah, is just a product, yeah, of two signed cardinal function, where the argument, yeah, is pi zeta zero u, and here pi zeta 0 times v. Okay, now I will just lift up everything a little bit. So we expect now that the visibility of the fringes, you remember the visibility is a module of the complex degree of mutual coherence. Yeah. So we will have to take the module of this expression, and we find how the visibility of the fringes for the case of a square star should depend on the frequencies u and v. Now, well, what we see is that, well, this quantity, I said before, can be a complex quantity, but in this case, we find that it is a real quantity, and the reason is that it's because the square star is symmetric, and anything symmetric, will give rise, to a real expression for the complex degree of mutual coherence, This is the reason, Now, as expected, when will the star be resolved? Well, when the visibility will be equal to 0, And for the visibility to be equal to 0, we find here that either this argument should be equal to pi, because the sign of pi is equal to 0, or the argument of this sign function, So, this is what is shown, just below. I lower the screen. So we just said that the argument of the sign function, so pi times 0 times u should be equal to pi. Now we have a nice simplification. We find that zeta 0, so the angular radius, well, the angular side of the square is equal to 1 over u, but u is the space frequency is x over lambda, Okay, so this is one condition, or that zeta 0 is equal to 1 over v lambda divided by y, And what we find here, you remember that lambda over b, where b is the baseline, was the angular resolution of our interferometer. And here also we find that we resolve the star, when the visibility gets equal to 0, and if we observe such a null visibility, we know that the angular, well, the angular radius of the star, of the square star, is just equal to lambda divided by the value of the baseline, which is either x or y in this case. Now, well, let's make use of GeoGebra to visualize these results. So I just use GeoGebra. Okay, I'm coming here. So this is a representation of the star, which is a square in the sky, And now I try to get the video illustrating the visibility for that case. So just put it here. Hope it will work. Yes. Now, this one will move away. Now, I try to move a little bit the screen. It's not, it doesn't work, doesn't respond. This is my worry, but it happens, So what I will do, I still give a try, Okay, now it's already a bit better, but I would like still to move it a little bit up. Okay, now it looks okay. Now it's too much. Maybe I'll move this one away here. Maybe just move a little bit this on the right, but we just have to be patient. So anyway, what is shown here, is expression of the visibility as a function of UV. So you find here, the sign of pi zeta 0 u divided by pi zeta 0 u, in times the sign pi zeta 0 v divided by pi zeta 0 v. And what we see is that, well, it has positive and negative values, yeah. So the maximum is reached for u or v equal to 0, and it gets to 0, yeah, whenever the value of u or v is equal to +1 or -1. Yeah? Okay. Now I may start the video. I just touch here. So the video should start in a moment, I hope. Well, in fact, the video, well, if it would work, yeah, would show you, yeah, the representation, yeah, of this function in 3 dimensions, yeah. And here below, yeah, I've just set the module, yeah, of that representation. Oh yeah, now it works. Yeah. So you see here the 3D view, yeah, of the complex degree of mutual coherence of the function. Yeah. Okay. It stopped suddenly. The reason is that probably, you know, the system, yeah, is responding very slowly, but it should start again in a moment. Yeah. Okay, so it continues. Yeah. So you see it from different sides. So this is a complex degree of mutual coherence. And now, well, we should just pass to the module. And to the module, of course, you only see positivity. Yeah, we see that the module, yeah, gets to 0 whenever u or v is equal to -1. You can see it on the display. Yeah. Now I just change the value of zeta 0. I increase it, yeah, to another, well, larger value, and then we see more side lobes, yeah, in the complex degree of mutual coherence. And in a moment, yeah, I will show again, yeah, the module, yeah, and we see that, well, it gets null whenever, yeah, u or v is the inverse of zeta 0, yeah. And so, well, if we would assume that all the stars in the sky, yeah, are square, what we would do, we would try to look at the stars, yeah, with a short baseline. And when the baseline is too short, yeah, the visibility would be equal to 1. And we would increase the baseline, yeah, until we would see a decrease in the visibility. And if the star would really be square, well, even a single measurement of a visibility equal to 1 would give you, yeah, the information as to what is the size, the angular size of the star. Okay, so I'll end up here now, yeah, and we can I can go to interaction, yeah, with those of you, yeah, who have questions, yeah, on that lecture or on the previous lecture. So could you see the video clearly?
Yeah, I think it worked out fine. Yes.
Yeah. Okay. So anyway, yeah, I'll send to Prakash, yeah, the video, yeah, and the PDF file, yeah, that I have just shown, yeah, on the screen, and well, you will just you know, upload the documents, yeah, on the forum page. Yeah. So I'm ready now for the questions. Yeah.
Okay. So as you know from previous times, you can raise your hand. I've already set it so that you can unmute yourself and ask a question if you want. Other than that, you can also, if your mic doesn't work for some reason, you can type it on the chat window. Okay, Saraswati, you can unmute and ask.
Okay, I don't know if I'm confusing the concept, but if we have a uniform circular shape in the sky, a star or whatever, then in the visibility, we would have like a 2D sinc function. And we say that when we resolve the source, the visibility goes to 0 and the fringes are washed out. So if that happens, how does the visibility like rise again? Like how do we get fringes again? Like
yeah.
Yeah.
Mm-hmm. Yeah. Well, for the case, yeah, of a circular source, yeah, you agree that you would not see a sinc cardinal function, but you would see a first order Bessel function, yeah, but which is essentially, yeah, a airy disk kind of function, yeah. And well, what happens, yeah, is that in fact, yeah, if all the stars would be circular disks, yeah, uniformly bright, yeah, in fact, just one measurement, yeah, of the visibility non being equal to 1 would suffice, yeah, to provide you the real angular diameter of the star. Yeah, it's because a priori, yeah, you would say, well, the model, I know what it is. Yeah, it is a first order Bessel function. Yeah, and because of the symmetry, I know that just with one baseline, which would slightly resolve the star, yeah, I would be able, yeah, to fit, yeah, the Bessel function for that point and get the value of the angular diameter. Yeah. Now, your question is that, yeah, when I look at the star, if the baseline is too small, what happens, yeah, the visibility is very high. Then when I increase the baseline, yeah, the visibility decreases, yeah? Well, just because of the interference, yeah, okay? And at a certain time, well, there will be non-interference, yeah, resulting in the fact that you will not see the fringes anymore, yeah? But now, when you will still increase a little bit, yeah, the baseline, yeah, you may still get, yeah, well, a very small amount of interference, yeah, coming up again. Yeah? Well, it's just what we observe, but the visibility will rise just a little bit, then goes to zero, still a little bit, and goes to zero. And this will be very difficult to measure, yeah, because the amplitude, yeah, the modulation, I mean, of the fringes, yeah, will be so small, yeah. But yeah, I mean, why? Yeah, it's just like when we are observing a star with a single aperture telescope. Yeah, you agree. We don't see just a central dot of light. We see a central dot of light surrounded, yeah, by a first dark ring, where I mean, there is no more light. And if you go a little bit farther out, yeah, you see side lobes again, yeah. And it's because, well, there is still a fraction of light, yeah, from well, different parts of the mirror, yeah, which is interfering, but quite badly, yeah, because well, it doesn't provide, yeah, interesting information, yeah, for the angular resolution of your interferometer. And in the case of the star, it's exactly the same, yeah. When it may come to a point when the visibility gets to zero, and we know that we have resolved the star, but when we increase the baseline, well, it can be that for that particular configuration, yeah, there is still, you know, some possible residual interference, and it's why, you know, the VDP slightly increase again. Yeah. Yeah, did I answer your question?
Sort of, but like, I mean, my thing is like, when we resolve it, we're saying that the source is made up of many number of point sources which are not coherent, which is why we don't get fringes and which is why our visibility goes to zero. So if our visibility is again rising, even by a small amount, does that mean that there is some amount of coherence between the different parts of the source that we have now resolved?
Yeah, of course. I mean, exactly. Yeah. So when, you know, just like with, just in terms of a single pupil, yeah, not an interferometer, yeah. So what we see in the focal plane, yeah, is not the central dot of light, yeah. It's an airy disk, yeah. So in the center, yeah, we have well, a peak of light, then surrounded by a first minimum, yeah. So the dark circle, and then we still get, yeah, some residual light, yeah, and it's because there is still some interference, yeah, in the case of the mirror, yeah, between different area of the mirror, yeah, light coming from different parts is still positively, yeah, interfering, and it's the same for the star, absolutely. Yeah.
Okay, thank you.
Yeah, with pleasure.
Jean, there's a question in the chat.
Yes.
It's sort of long.
Oh, is it
hopefully
the
you can
last,
read it out.
the last question?
Yes.
Or can we discuss how to physically interpret visibility as a Fourier space of intensity distribution? I'm not able to get the physical field. Maybe like compare with case of point source, where we see that intensity and dimension of aperture are Fourier transform of each other. Complex degree of coherence rise due to finite size of the source. What will it be if we look at the limit point source? Yeah. Well,
She has also raised her hand. Maybe.
Yeah, can I can now talk. Initially, my microphone was not responding.
okay.
Sure, go ahead.
So, I'm sorry. Actually, it's a bit long. I was just trying to I was getting confused between what really is this visibility function, because when we talk about interference, when we deal with point sources, then it's easier to see that if you take a Fourier transform, I mean, you can see the interference pattern or the intensity distribution as a Fourier transform of the dimensions of your aperture or things like, or anything like that. I am not able to see that this idea of degree of this mutual incoherence, the degree of mutual incoherence arises because of finite size of the source, as I can understand it.
Yeah. Yeah.
So
Okay.
I was
Now,
not able to physically visualize this idea of seeing it as a Fourier transform.
yeah.
How to see this concept of visibility? Somehow, since we're not used to dealing with visibility, otherwise, I'm finding it a little difficult to understand how to function
Can I
visibility.
add something?
Yeah,
Yes,
Dev.
sure.
Okay. Yeah. So what one is trying to measure on any baseline is the level of similarity of the electric field received, okay, or electromagnetic field received. That similarity vanishes or increases depending on the superposition of fields received from various components of the source or brightness distribution in general, and the other version received by the other telescope or other element, which is the same ingredients but differently phase shifted. So you can imagine that it's a final play between the phase relationship between the fields received at two different locations. And superposition of those is what we are looking at. There is no coherence between one point in the sky with another point in the sky. The coherence is seen in the electric field received at the two locations, which is superposition of electric field, electromagnetic fields received from every component of the source. Each one of them interacts and checks its similarity with the corresponding component of the electric magnetic field received by the other element. The assessment of that will be available as a complex quantity, basically amplitude and phase. And now these amplitudes and phases are going to superimpose, and they can cancel sometimes, they can cohere and increase to give you maximum output, which is what we call visibility.
Yeah. Now, well, I mean, okay, this is one vision of the situation, which is absolutely correct. Yeah. And well, another way, yeah, to see the things, yeah, is the following. Yeah. Well, you may, if you take, yeah, two apertures, yeah, well, the two aperture, yeah, receive a train of waves, yeah, with the amplitude being modulated, yeah. And what you definitely want, yeah, is that these two groups of waves, yeah, arrive at the same, well, at the 2 points, yeah, with a time difference, yeah, which is smaller than the time of coherence, yeah. And you know that, well, it's easy, yeah, that these two two trains of waves arrive at the same moment, you know, if the baseline is small, but as you extend the baseline, yeah, well, the time difference increase, and at the moment, yeah, the time difference between the arrival of these two wave groups, yeah, will be larger than the time of coherence, and then it's impossible for them to interfere, yeah, and this is why you will lose the coherence, yeah. But so, well, this is just intuitive presentation, but I agree with absolutely with what Professor Desch, yeah, told just before me, yeah. Yeah, this is just complementary perspectives, yeah. Yeah, and now, well, you know, to understand everything very simply, yeah, just take the case, yeah, of a single aperture, yeah. And well, for this single case of full aperture, yeah, you understand, you know, how the image is formed, yeah. And now, on that aperture, what you can do, just put a mask, yeah, with two holes, yeah, and just try to follow, yeah, the two trains of waves coming from these two holes, and see under which condition, yeah, you may get coherence or not get coherence, etc., etc. Yeah. So what one has to make, yeah, the exercise oneself, yeah, because I know that it's not very often, it's not sufficient, yeah, when you hear an explanation coming from somebody like us, you know, like Professor Desch or myself, yeah, but just try to make the situation very simple by considering the case of a single aperture, full aperture. So it's a converging lens, yeah. But then you isolate, yeah, on that full aperture, two small holes, yeah, and try to see what's coming up, yeah. And then it's very funny to understand, because then it's easy to understand why you get a hairy disk, yeah. It's just all the possible combination of two holes by two holes which are interfering, yeah, and gives rise to the hairy disk, yeah. But it's a very nice subject, you know. But one has to devote a lot of attention, yeah, with the brain, yeah, to really understand, and it's a very nice field, yeah, yeah. So is it okay?
Yeah, right. Thank you.
So any more questions?
Yeah, as time goes on, yeah. Well, I won't forget, you know, the question you're asking, and if I find some simple visualization, yeah, with a figure, yeah, to make things much more simple to understand, I'll do that, yeah, because very often, you know, when you understand very well a concept, yeah, it's possible, yeah, to show it with a single picture, yeah, yeah. I try to do that for you. So more questions?
So I want to clarify one thing, Jean.
Yes.
So because the baselines generally tend to be longer than the coherence length scales, right?
The what? Can you repeat? The what?
The baselines of our interferometers.
Yes.
They tend to be larger than the coherence length, and we still at the focal plane try to ensure that the waves that are interfering have wavelength separations or path length separations less than the coherent length by introducing extra path lengths in the system, right? Like the one that you show behind. So the picture behind is the one that increases the path length. Is that correct?
No, it does not. Well, it increases the path length, yeah, along one light beam to compensate, yeah, for the difference in the length of these beams, yeah, coming from the star, yeah. So when the two beams arrive in the focal plane, yeah, they are just about in phase, yeah, correct. So the time delay between the arrivals of the two beams coming from the star to the focal plane is almost equal to zero. Is less than the time of coherence. So, well, I'll explain that, you know, during, I think the next lecture, yeah, during the next lecture, I'll show a diagram, yeah, showing exactly, you know, how we compensate, yeah, for the difference in path lengths, yeah, with delay lines, yeah. So just forget, I mean, this question for now, yeah? We'll come
Yeah,
to it
sure,
yeah,
sure.
during the next
Okay,
lecture.
sure.
Yeah.
Yeah, but I think I understand it. I mean, it
Yeah.
was my assumption anyway.
Yeah.
So Priyanka, you have a question, you can unmute yourself and ask.
Thank you. Jean, so I have one question that when we consider geometric dilution,
When
so
you
it should be
consider what? When you consider what?
geometric dilution.
Yes.
So that should be considered either it is a point source or extended source. I mean, it should be independent of that, right?
Yes, of course. Yeah.
Okay, I just got confused from some formal calculation in the notes. So when you are doing for point source, you have written the amplitude as small a, but when we were doing for extended source, you explicitly mention it that the amplitude would be 1 over r, and that's why the intensity would go 1 over r square.
Yes.
So I mean that would be done for the point sources as well, right?
Well, it would be exactly the same. Yeah. Well, you could consider that the point source is also composed of many surface elements which goes
Tends to 0.
to become extremely small. Yeah. Infinitely small. Yeah. Yeah. So the same argument holds for point-like
Point
source.
source.
Yeah.
Okay.
Yeah.
Thank you, Jean.
Yeah. So well, I insist. Yeah. That there is a forum. Yeah. And if you have more questions coming to your mind, and there should be many questions because, well, I mean, it's a very rich field, and well, many questions may arise in your mind, so don't hesitate, to send your questions, and well, I've seen that some of the participants, were very active in replying, in providing answers, so that the job for us is very easy, so I think that well, but we would expect to get more people get involved in the forum. Don't be shy, don't be afraid.
Yeah, there is a simple analogy one can think of to demonstrate how the visibility falls down and then can increase again, or why it falls down for a broad source. Using a very familiar situation to everyone, which is we say stars twinkle, planets don't. Exactly same situation. Here, instead of the interferometer fringe, you have the diffraction pattern of the intervening atmosphere producing the corrugation. And so you will find that superposition of such twinkling patterns from each one of them, which are roughly similar but shifted, can superpose to give cancellation to produce reduced twinkling when the source size becomes broad, as in planets.
Yeah,
it's the same phenomena. It's although it's a random diffraction pattern there, here it's more systematic because of the two clear apertures defining the pattern.
That's a good analogy, Desh.
Yeah. Now, well, an interesting question for the participants is the following. Well, let's just think that you have an extended star and that you are working in, well, just emitting coherent light over the whole source. And it is extended. It's not point-like. So would the results that we have derived still be valid or not? And so this is my question to the participants. And well, if any one of you have got some hint or some ideas for the answer, just go on the forum and let's have some exchange on that. So the idea is, well, would still the module of the complex degree of mutual coherence be valid for a star which is extended, but for which light is absolutely coherent over the whole surface? So could we still use that technique to derive the size of a laser star, but with some finite angular extension? Sure. We will pose that question in the forum.
Yeah. So any other questions, or should we wait some more, or should we wrap it up?
Yeah. Then, well, one thing I tried to set in the video, which I didn't show today, yeah, is the fact that you may represent the complex degree of mutual coherence, yeah, as being the product, yeah, of its module and by the complex exponentiation function, yeah, of I time a phase, yeah, a phase, yeah. And in fact, what one can demonstrate very easily, yeah, for the case of a symmetric source, yeah, is that this phase, yeah, is either equal to 0 or is equal to pi, yeah, and there is a jump. You go from 0 to pi and pi to 0, yeah, and well, the way to get this information is just to say, well, in the case, yeah, of a square star, we saw that we had two sine cardinal functions, yeah? And you could say, okay, the sine cardinal function is equal to the sine cardinal function divided by the module multiplied by its module, yeah? Because if I divide and multiply by the module, it remains the same. And now, well, in this case, yeah, the sine cardinal divided by its module would give the sine, in fact, yeah, of the sine function, yeah, the sine of the sine function, yeah, which would be either equal to +1 or 2 minus 1, yeah. And when in the complex representation, yeah, the way to represent +1 or -1, yeah, is just a cosine, yeah, cosine of pi or cosine of 0, and this is equal to exponentiation function of I multiplied by phi, where phi is either equal to 0 or to pi. Yeah, but I try to include, yeah, this result, yeah, in the video presentation that I'll dispatch here to Prakash, yeah, to set on the forum page. And later on, yeah, when you would consider non-symmetric sources, like, for instance, yeah, a double star, which flux ratio is not equal to 1. Yeah? So this would be an asymmetric distribution of light in the sky. And then you would see that in that case, the complex degree of mutual coherence, yeah, is a complex expression. Yeah? And what is quite fantastic is that with the interferometers, yeah, it's possible, yeah, to retrieve some information about that phase, yeah, the phase of the complex function, yeah, which gives you some information about the source structure, yeah. And but it's not easy to do, to retrieve that phase information. Well, it was very easily done in the radio domain, yeah, and more difficult, yeah, with optical interferometers. But we'll see during some of the next lectures that whenever you have 3 apertures, yeah, it's possible, yeah, to retrieve some very interesting information, yeah, about the source, phase information, using the technique of phase closure, or sometimes called closure phase, yeah. But this will be a subject for the future, not for now. So in the meantime, more questions? I'm not sure.
No.
No. So I propose that in that case, we may just stop here, yeah?
Yeah.
And continue, yeah, possible discussions, yeah, on the forum page, yeah? And thanks for those participants, yeah, who are, you know, answering, you know, some of the questions raised by others, yeah? So it's nice, very nice to see those exchanges, yeah?
Yes.
Yeah, and Prakash, could you tell us something about the next quiz when it will arrive?
Yeah, the assignment is pretty much ready. I'm just taking it up. So this week, in a day or two, it should be available.
Oh, yes.
Quiz and assignment, both. Okay, shall we just wrap up? Yeah.
Yeah, absolutely, yeah. So So next lesson, right? A lecture, if I'm not, I'm not sure. Maybe Professor Desh, could you tell us when you think will be programmed your presentation?
Yeah, I hope to start this Wednesday.
Mm-hmm.
Uh,
So it would be the same time, right?
Wednesday, 2 o'clock. Yeah, correct.
Yeah.
I think somebody has a question, Saraswati Kalyani.
Yeah, I do actually. It's about the analogy that you gave about how planets don't twinkle whereas stars twinkle. But in that particular case, it's not a property of the source. It's a property like because of the observation that we are doing, like as in the atmosphere. Because of the atmosphere, there's turbulence, and that's why the twinkling effect comes into picture. Whereas when the visibility drops and increases, that's actually like a property of the source because the visibility is the Fourier transform of the source intensity. So I don't get how the two are the same.
Okay, so I think you correctly said that the pattern that you get is a property of the whatever produces that pattern, which is not the source. And in our case, that pattern is produced by the way the phases are compared, okay, for an individual component of the source by our instrument, correct?
Yeah.
Depends on the baseline and so on and so forth, right?
Yeah.
Okay. So that will decide the phase relationships, much the way the diffraction pattern will. Now, where does the source property come in? The source property comes in the way the brightness distribution is there in the source. That means how the brightness is distributed in the source. And that is what is different between the star and the source in terms of angular distribution. Okay.
Okay.
And that produces each one of the components. You can imagine planet, the way it will appear is made of star-like specks, each one of them giving you 100% twinkling. Okay.
Okay.
Now these twinkling patterns, because of the shift in the direction, each one of the points is shifted from some reference direction, correct?
Yeah.
And that causes the shift of the pattern.
Okay.
And that pattern shift gives you different manifestation or different version of the same twinkling pattern. Now just imagine you take any fluctuating pattern and move it by small amounts relating to the shifts of the components of the source, the way they are shifted from a reference direction, and add them. Won't you see the fluctuations going down in proportion?
Yeah.
Okay, so what it is. Okay. Individually, the property of the imprint of the pattern associated with either the telescope or the diffraction pattern associated with the turbulent atmosphere, they are not the property of the source. Property of the source is the way brightness distribution is distributed. I mean, the brightness distribution it has. And that will decide depending on the angular shifts, it will decide how shifted the version will be added of this pattern.
Yes.
And when you add such things with different shifts, any oscillating or fluctuating pattern will reduce the amount of fluctuation in proportion, okay, as a percentage fluctuation.
Okay.
In fact, there is, since we are on this topic, I heard comments from some of you while asking the question. There might be some confusion about the coherence across the source versus coherence in the mutual coherence that we would see as a spatial coherence on the Earth, right? So that is a measure of similarity of signals we received at the two locations.
Yeah.
This should not be confused between any coherence between two components of the sources. Okay, there is no coherence. All are incoherent sources. Okay,
Yeah,
the
so
sources
that's the
across
thing. So,
across angular spread, they are made of incoherent sources.
yeah, so that exactly is my doubt. So since we are saying that no 2 points on the source can be coherent, how can
Correct.
we have any visibility, like any non-zero visibility, once we've resolved the source?
Okay, so when we receive something, we ask for that point, for a given point in the source, what
Okay.
is the similarity of signals received at the two locations we are measuring. Okay,
Yeah.
we get an answer.
Hmm.
We get an answer with a phase, as a complex number, right?
Yeah.
That complex number does not depend on either our specific location. It depends only on the separation of the two telescopes.
Yeah.
Right? And it will depend on, of course, the angular shift, okay, of that point we consider in the source from the reference direction, because we would have compensated for delays only for the reference direction. We cannot
Yeah.
simultaneously compensate for delays for all directions in the sky.
Yeah.
Okay. So having done that, because of remaining uncompensated path delay, okay, for that source which is away from the reference direction, we will have some phase shifted version of the pattern that we have. Now this pattern is not using any information about the phase of the electromagnetic wave, okay, received. It is using information only about the relative phase of the electromagnetic wave received at the two locations.
Yeah.
Which is simply a function of the angular shift of the point that we consider away from the reference direction and separation and relative orientation of the telescope baseline.
Okay.
So we have not used any information about any phase relationship between one speck of the source with another speck of the source.
But
there are some peculiar situations in the sky, where images of the sky can be, images of a particular source can be seen, and they might have some level of coherence and so on and so forth. But those are very complex situations.
But if we have two different points of the same source within our field of view, then we would get electromagnetic wave from both. And as an observer, we can't say that this wave is from this point and the other wave. Like, it's going to be mixed when it comes to us. So
yes, we cannot resolve. Correct. But when you check the similarity, when we take the sum, which we cannot distinguish, and we multiply it by the complex conjugate of the same sum to get the intensity, to check the similarity, you can do the math sum. You will see, if let's call it A and B, you will get AB, you will get A star and B star, right?
Yeah.
You will also get B star.
Yeah.
And A star B, right?
Yeah.
And you can show that the entire interferometry and the Vansittart-Zernike theorem works because of A, B star and A star B on the average go to 0.
Okay. Okay.
So what remains is only A star and B star, and there we have not used of any phase relationship between A and B.
Okay.
Yeah, well, I propose that, if any of you, may show a simple picture, to answer, the question which was raised now, which just to have a, very, very simple view, on what's going on intuitively, you're just welcome, I try to participate to that too, because, well, everything what has been said, is correct, but I'm not sure that everybody, got it right,
Okay.
So shall we continue on the forum, right?
Yes, I think we should.
Yeah, this is good. Well, yes, the question, yeah, was very basic and very important, yeah, because when you get convinced, yeah, by, well, the argument presented by Professor Desch, yeah, and if you have the right picture in your head, yeah, then well, it will clarify many things, yeah, for the rest of the subject, yeah. So we ended up right now, okay, fine. So I just greet everybody, yeah, and so Professor Desch, normally, yeah, we will see you on Wednesday, yeah, at 2:00, yeah, yeah, if it is confirmed, yeah, yeah, we understand.
Yes, sure. I look forward to that. Yeah.
Yeah.
Okay, thanks for joining everyone. Bye.
Bye bye.